All right. This video is going to be the notes for sections 5.1 and 5.2. And let's just call it analyzing functions using both the first and second derivatives of that function. That's not exactly what the sections are called in the book. Actually, they're called what? Analysis of functions 1 and 2, and then they describe that a little bit. So, the first thing that we have to do here is figure out what the second derivative means. And maybe just before we do that even, we can remind ourselves some things about the first derivative. So, if the first derivative of a function is greater than 0, then we can say that f of x, if you think about that for a second, if the slope is greater than 0, then that means the function is increasing. Likewise, if f prime of x is less than 0, that means the function is decreasing. Excuse me. Now, what about if it's 0? I mean, this is greater than 0, that's less than 0. What if it actually is 0? Well, this will be our first definition here. If f of x is 0 if f of x is equal to 0 for some value x equals c, then we say f of x has a critical point at x equals c. So anywhere where the slope is 0, oops, that's supposed to be f prime of x, sorry. Anywhere where the slope is 0, we call that a critical point. Also, if f prime of x is undefined at x equals c, this is also a critical point. So a couple different ways you can have something what we call a critical point. You can have a place where the slope is 0, or you can have a place where the slope is undefined. Now, that doesn't mean somewhere like a jump or a vertical asymptote. We're talking about somewhere where the derivative does exist. Where the original function does exist. So it doesn't really make sense to ask what's the slope of a function at a place where it's got a vertical asymptote, because the function isn't even defined there, right? So just be careful about that. Now, what does the second derivative mean? Well, I'll give you another definition. If the second derivative of a function is positive somewhere for the function, we say that the original function, the original function is concave up. Concave up at that location. Concave up. And if the second derivative is negative, then we say, you guessed it, that the original function is concave down at x equals c. And those are pretty much all the definitions that we need for section 5.1. And I think I'd just like to talk for a few minutes about what all this looks like. So, for example, what is this? I mean, we know what increasing and decreasing mean. That's not any big deal. But what is this concavity business about? Well, let me make you a little chart here. And should certainly reproduce this whole chart in your notes. I'm going to make a chart of all the different possible combinations. So up here at the top we'll put this can be the sine of the derivative of the function. And over here I'll put the sine of the second derivative. This is something that you want to be very familiar with, what these look like. Okay, so we'll do positive, negative, and then what if it's actually 0, and then here positive, negative, and what if it's actually 0. All right, so in this box here, we want to try to make a little sketch of what a function would look like if its first derivative was positive and its second derivative was also positive. Well, first derivative positive, that just means it's increasing. What does it mean for the second derivative to be positive? Well, that's like the derivative of the derivative, right? So if the derivative of the derivative is positive, that means not only are the slopes positive here, right? Not only is it going up, but as we go from left to right, the slopes are getting bigger. It's getting steeper. So that would be something that looks like this, right? It's going up and also bending up. This idea of concave is kind of like which direction the function's bending. So it's bending up. And then let's see, how about if the function were increasing? So the sine of f prime of x is positive, but it's concave down. Well, it's still going up, but the slopes are decreasing. The sine of f prime of x, that's the rate that the slopes are changing at. If that's negative, that means the slopes are getting smaller. So although they're still positive, they're getting smaller, something like that. Right? We start out with bigger numbers and they're getting smaller. That's what that sign of the second derivative tells us. Right? So those are both increasing. This is increasing concave up. This is increasing concave down. All right? And then what if it's increasing, but the second derivative is 0? Well, if it's increasing and its second derivative is 0, it could be a straight line, right? Because that has no bend to it at all. The second derivative of that would be 0. The slope's not changing at all. But maybe more interestingly, we could find a function where it's increasing and then just for a minute, so here's a little bit of a function, and you can see how this function is increasing all the way through here, but it's going from bending down to bending up. And right here, we have a place where it looks like it changes from concave down to concave up. And that means it has a second derivative of 0. It's not flat here. This is not where the tangent line is horizontal. It's going from, and we could likewise go from bending up to bending down. Right there. That would be a place where the second derivative would be 0. Right? Because it's going from being positive to negative here, and here negative to positive. Bending down to bending up. And here we have bending up to bending down. So that's an example. We'll name those. I'll give you another definition in a few minutes. We'll talk more about that. Now, Here, let's fill in these. So here we have a function that's decreasing, but it's concave up. So it's going down, but it's bending up. So that'd be something like this, right? It's going down, but it's bending up, like a mirror image of this. Here's a function here that's going down, and it's also bending down. So going down and bending down. And here, same idea with these. We have a function that's going down like this, and a function that could also be doing it like this. Oops, that's the same thing. So something like this. So there's a point in the middle here where this goes from bending up to bending down, and this goes from bending down to bending up. Right? So you can see the functions are decreasing, but they're changing their concavity. And as it changes from positive to negative, it must pass through 0. So that's what that looks like. All right. How about a function where the first derivative is 0? In other words, it's got a 0 slope tangent line, horizontal tangent line, but it's concave up. Well, that would be like, right, here's a function that's bending up, but at that point right there, the slope is 0. Likewise, here's a function that's bending down. Right, there's a slope of 0. And here, how about a place where the first derivative is 0 and the second derivative is also 0? There's different possible examples of this, but I think maybe one of the most instructive ones would be something like this, like the x cubed function, where we've got, right here, we've got a place where there's a horizontal tangent line, so the slope would be 0, and it's also changing from bending down to bending up. So there are some examples of different types of situations, what it means for one of those things to be 0, and also what it means for them to be the different combinations of positive and negative. Now, our book calls a genuine maximum or minimum. They call that a place where the derivative, I don't want to go into the definition. I'm not going to write it down because we don't use this definition really, but for matching up answers to the back of the book, just in case it comes up, they do introduce an extra term which they call a stationary point, which is a maximum or minimum where the derivative really is equal to 0. Okay, so just in case you run into that. So let's talk about some examples, different types of situations you might see. You could see, for example, here's some like sort of unusual examples. How about a function that looks like this? Well, that would be a maximum there, right? I mean, it's clearly a maximum of that function. But notice that the derivative there is undefined at that point. It's undefined right there. So it doesn't always have to be equal to 0. And that's a little tricky thing that, that does get us into trouble sometimes. With particular functions, I'll try to give you an example of that in a few minutes. Now, I'm going to define one more thing. An inflection point is a point where the second derivative turns from positive to negative, or from negative to positive. In other words, it changes sign. Now, this usually happens where the second derivative is equal to 0. But it can happen where the second derivative is undefined. Okay? Usually it happens where the second derivative is 0, but it can happen where the second derivative is undefined. And just because your second derivative is equal to 0, that is not a guarantee that f of x has an inflection point. It's a good place to look, but you have to check and see if the signs change. Okay, so I think that's enough of the background information here. I think we should do a couple examples so you can see what these problems, what kinds of things you're going to be doing. So here's an example. I want you to find the intervals of increasing, decreasing, concave up, concave down, and identify maximums, minimums, and inflection points. All right? Excuse me. Now to find increasing, decreasing, and maximums and minimums, we look at the derivative, the first derivative. Oh, sorry, I forgot to tell you for what function. Inflection points of, kind of need a function, don't we? Of, let's do f of x is equal to 3x to the fourth plus 4x cubed minus 12x squared plus 2. Okay, so again, to find increasing, decreasing maximums and minimums, we look at the first derivative. So the first derivative would be 12x cubed plus 12x squared minus 24x. Right? Now we're interested in where, for increasing and decreasing, we're interested in where this is positive and negative, and for maximums and minimums, we're interested in where it's equal to 0. So what I'm going to do is set this equal to 0 and see if I can identify those points where the sign changes. Right? We're all about where the sign changes here. Now I'm going to factor here. It looks like I can factor a 12x out of this. If you're thinking there's going to be some algebra involved in this chapter, you are right. And that further factors into x plus 2 x minus 1. This, you might be thinking at this point, this is not just any old polynomial that I made up. It was carefully crafted so this would factor. If you just made up a polynomial, chances are it's not going to factor nicely like this. So that means we have, looks like -2, 0, and 1. I put them in order from smallest to biggest. Okay, and then what I'm going to do is make a sign chart for the derivative of this function. What that means is I'm just going to make a little map here of where the possible places the derivative changes, and it doesn't really matter if it's a scale. One might be a little too far out there relative to that, but whatever. Okay, so now look, here's the derivative, right? I want to plug some numbers in and see, like, what's going on down here. Is it positive or negative? What's going on in here? What's going on in here? These are the places where it's 0. So if it's going to change sign from positive to negative, it's going to do it at these values. Okay? Notice that this, and this are all forms of the same thing. So when you pick an x value, like I'm going to pick something down here, like try -3. So -3 can be a representative for this zone. I'm going to plug it in this version, because all I care about is positive and negative. So -3 times this, that's negative. -3 plus 2, that's negative. -3 minus 1, that's negative. So I got negative, negative, negative. That gives me a negative when I multiply those together. Okay? I'm going to pick a representative x value in here between -2 and 0, like -1. Plug it in here, that gives me negative, positive, negative. Negative, positive, negative. That's positive. I'm going to pick a number between 0 and 1, like 1/2. So that gives me positive, a positive, and a negative. Positive, positive, negative. And then I pick a number above 1, like 2. Positive, positive, positive. So that gives me this. Right? So they alternated back and forth. Now, don't just think that this means every single time all you have to do is find one, and then they're going to alternate. That's not true. Sometimes you get a couple positives or negatives in a row. And we'll see an example like that pretty shortly, I think. So what does this mean? Well, this means the function is increasing well, that's when the derivative is positive, right? So it's increasing from -2 to 0, and also from 1 to infinity. It's decreasing from, let's see, -infinity to -2, and from 0 to 1. Now, if it's decreasing and then increasing, then this that's a minimum, right? Negative to positive, and negative to positive, that's also a minimum. And a maximum here, where it goes from increasing to decreasing, increasing to decreasing. All right, so that takes care of that first derivative stuff. And then to find concave up, concave down, and inflection points, we're going to look at the second derivative and play the same game. So let's see, there's the derivative. So the second derivative is 36x squared plus 24x minus 24. Right? So I'm going to set that equal to 0 because I'm interested in where this changes sign. So probably changes sign when it goes through 0, right? So let's see. It looks like I can factor out a 12. 12 times 3x squared plus 2x minus 2. And playing around with that a little bit, I think that it does not factor. So that means my solutions are going to come from the quadratic formula. Opposite of b plus or minus the square root of b squared minus 4, there's a minus sign there, so that's going to make that positive, right? Minus 4ac all over 2a. So let's see, that's 4 times 2 is 8 times 2, this is 28. I'm going to take that all the way home. I don't know, you could write it like that. You could write it with a big 3 on the bottom, something like that. So, I mean, where's that? I don't know. But certainly we know that that one is smaller than this one. So not pretty, but we can try those. Now I guess we just need to be sure when we pick numbers that we really do pick things that are like smaller and whatever. I think clearly this is bigger than negative 1/3, so this is going, 0 is in between these, right? And then I just think we need to pick things that are big enough. And what you'll find if you try that, you're going to find that this function is concave up, because when you plug a number down here, like negative, just to be sure, you got to make sure you're below this. So let's say -5. Put a -5 in here, you're going to find that you get a positive. Then plug 0 in, you're going to get a negative, and then plug a big or positive number in. Like you convince yourself pretty easily that that's going to be positive there. So here are our intervals of concave up and concave down. So we're concave up from -∞ to -1/3 minus the square root of 7/3, and -1/3 plus the square root of 7/3 to infinity. Sorry, you can't see that, can you? There. And then it's concave down on that little interval in the middle. Oops, that should be minus, and then that should be a comma. Sorry about that. Right, just in between those. And they're inflection points. Inflection points at x equals those two values, -1/3 minus the square root of 7/3, and x equals -1/3 plus the square root of 7/3. Right? That's a lot of stuff to say about one function. Let me just point out here that these are inflection points not just because they're the zeros, but because it really does change from positive to negative and negative to positive. If you get two positives in a row, it's not an inflection point. All right. Well, this is shaping up to be a long set of notes, but I do want to do one more example for you. And I'll apologize for the length of the video. Okay, so there's another function. F of x is equal to x times e to the negative x. And we're going to find all the same stuff, right? All the same intervals and everything. So same directions as the last example. Okay, so first we're going to examine the first derivative. Using the product rule, derivative of the first times the second plus the first times the derivative of the second. Now I'm going to set that equal to 0. And notice when I set that equal to 0, I can factor out an e to the negative x. All right, that's really the key to being able to see what's going on here. That leaves a 1 here and a negative x here. Now, where is this equal to 0? Well, if you look at this, e to the negative x, when's that equal to 0? It's never 0. Never 0. That's not 0 factorial, because of course that's equal to 1. It's never 0, exclamation point. Excited realization, not factorial. In fact, it's always positive or negative. Pause for a second and think about that. it's always positive. No matter what you raise e to, you always get a positive number. Even though it's raising it to the negative x, doesn't matter. Whatever you raise e to, you're always going to get a positive number. So the only thing that determines when this is equal to 0 is the 1 minus x. So that's equal to 0 when x is equal to 1. So make my sign chart for the derivative. Got to make these guys. Don't be lazy. And then we try some numbers. I try 0, but of course remember that this is always positive. I don't even really need to look at this. I just need to remember that it's always positive. So when I plug 0 in, this is positive. And when I plug something like 2 in, 1 minus 2, then this is negative. So what's going on here? This means this function is increasing from negative infinity to 1, and it's decreasing from 1 to infinity. And that means that this, increasing, decreasing, we have a maximum at x equals 1. Okay? Now let's do the second derivative, see what that tells us. So here's my first derivative. So I'm going to use the product rule on this version of it. I'm going to use this factored version because it's a little bit cleaner, right? It's the same as this, right? You could use this if you wanted to, but I'm going to use this version. So the derivative of the first times the second plus the first times the derivative of the second. Okay, now we certainly need to clean this up. We do want to set it equal to 0, but I've got to clean it up and see what it looks like. Actually, you know what? I can just factor. Well, let me clean it up first. There's a way of factoring it from here, but and if you can see what that is, then you can knock yourself out there. So that's that distributed to that. And then this negative times negative gives me positive, and then minus another one of those. So you see there's 2 of those. This is maybe too many steps to write out for your taste, but leave that up to you. Maybe you like to write out all these steps, whatever works for you. And now you can see that I can factor out an e to the negative x, and then I've got an x minus 2. And likewise, this is always positive. And this is equal to 0 when x equals 2. So let's make our sign chart for the second derivative. Only need 2 on there. And then I can test some numbers. It looks like if I plug into this version of the derivative here, that's my easiest version, I think, to work with. That's always positive. If I plug in a number that's less than 2, like 1, that's going to give me a negative. And if I plug in a number that's bigger than 2, that's going to give me positive. So that means we are concave down from negative infinity to 2, and concave up from 2 to infinity, which also means that here at 2 we have an inflection point because it really does change sign, right? Inflection point at x equals 2. And boy, I thought I could do that in a little less than 35 minutes. Well, I guess it is less than 35 minutes. So sorry that was so long. But that's a lot of information. This is a video I think you might want to come back and refer to as we make our way through the first half of Chapter 5. The first 4 sections of Chapter 5 are more of this. So please keep this video handy, keep these notes handy, and we'll build from here.